Who we have here, we have Sean Sall. He's with Arterys, and he's going to be talking to us about neural nets. So give him a round of applause.
Thanks, Jeremy. Appreciate it. And thank you guys all for joining me today. While I intro myself and talk about other random things, we're going to be working out of this repository today. So if you want to take the opportunity to load that up on GitHub, feel free to do that. It might make things easier and flow smoother and actually allow you to interact with the material today. So like Jeremy said, I'm Sean. I work for Arterys, which is a medical imaging company here in San Francisco. We focus on medical segmentation of MRI and CT scans for a number of modalities and a number of kind of parts of the body. I'm actually not focusing on the imaging myself. I'm on the machine learning team, but focusing right now on taking electronic healthcare records and predicting ICD-9 codes and mortality. We will be using neural networks for that at our company, which kind of lends itself to the talk today and is what I'm here to present on. So, as I mentioned, we're going to be working out of this repository. And effectively in this repository, what I've done is wrote what I'm calling a mini book that has 4 chapters. Today, we're going to walk through chapters 1 and 4. The general plan, I'm hopeful that this will actually work out, is that I'll talk for about half an hour. I'll give you guys 10 minutes to play around. I'll talk for another half hour-ish, give you guys some more time to play around, and then we'll do Q&A. But while I'm talking, don't hesitate to throw questions out there, raise your hand, yell at me, shout at me, get my attention in some way, shape, or form. So there are, before we dive in, 2 ways to follow along here. For any of you who are familiar with just cloning a GitHub repository, you can clone it with this command here, and then you'll have to edit your bash RC or your bash profile to add this repository to your path, because there are certain things that I've built in there that I'll access via that path. The second way, if you don't want to do it that way, is you can click this launch binder button, and it's going to run a Docker container on the back end, and that will allow you to just basically pull up my entire repository in a runnable fashion in your browser. So if you just click that, it's going to be a little bit slower than if you're running it locally, but I'm going to go ahead and click it now, and we'll go ahead and kind of dive in. So it'll take just a quick second or two to actually fire this up, but once we do, we'll have the entire repository as if I had just pulled it down locally and had kind of fired it up. If you run into any failed builds or other errors, I would just refresh the page. Occasionally, sometimes it's still a little finicky. Okay. From there, we are going to navigate into the mini books folder, and then the shallow neural networks folder from there. And like I mentioned today, we're going to be focusing on chapter 1, which is titled Simple Linear, and chapter 4, which is called Shallow Neural Network. And to give a high-level overview of what we're going to work through today, we're going to start with something that's hopefully much simpler and much more familiar, simple linear regression. And then we're going to take what we've learned there and take the kind of maybe neural network formulation that we're going to walk through and actually build a small, shallow neural network that's going to learn arbitrary functions. Give me a second real quick. I want to pull up for you that repository again and go to the README real quick, because I'm going to show you what our end goal is visually. So our end goal today is going to be to build a neural network that's going to be able to just basically learn arbitrary mathematical functions. Right? So we're going to build this neural network, and it's going to be able to take in some x values that follow a y equals sine x function, and then actually learn that function. It's going to be able to do that with cosine and tanh and some polynomial functions as well. So that's what we are working towards. Okay, so before we actually dive into the material, can I just get a quick show of hands? How many of you have some kind of programming background? Okay, fantastic. On a scale of 1 to 10, can you raise your hand if you'd rate yourself maybe 1 to 4, or like beginner stats math? Or okay, awesome. 4 to 7. Okay, right on. And then 7 to 10. Okay, cool. I think this is good stuff. Okay, so let's dive in, and I might take it a little bit faster then on some of the simple linear regression stuff. You can go ahead and choose the Python 2 kernel or the Python 3 kernel if you're firing this up. Either one should work, but give me a yell if it doesn't. Okay, so basically what we're going to do is we're going to start off with our standard simple linear regression, right? This is our equation where we have an intercept and we have a single coefficient and we're trying to predict some y. And we're going to basically just kind of think about it in a different way, okay? We're going to end up building this kind of computational graph that is going to denote every single part of our linear regression equation, and then we're going to code up a version of that computational graph and solve it using gradient descent. Another quick show of hands, how many of you are familiar with gradient descent? Okay, sweet. Cool, so we're going to take our simple linear regression equation, and before solving any problem with gradient descent, we have to figure out exactly what our cost or our loss is going to be. And so we're going to go ahead and choose squared error, right, as is common to use in simple linear regression. So this is going to be the error for an individual observation, and then if we wanted to sum across all observations, we'd have this following error. We'll real quickly note that if we were to solve, get our closed form solution for our beta 1 and our beta naught, this is what they would be if you solve for them in kind of a stats class, or just try to minimize the mean squared error by solving, taking the derivatives and solving. But we're not going to do that. We're going to solve with gradient descent. Before we do that, though, we're going to build our simple linear regression into a computational graph. How many of you are familiar with computational graphs? Okay, all right. A little bit less familiarity, but they're actually, I think, fairly simple. They are ultimately just, at least for now, a way that we can visualize these equations that we're talking about. So we're just going to try to visualize simple linear regression in this computational graph. That's what this picture here is denoting. So first things first, every single kind of piece of our linear regression equation gets its own node in this graph. And we have kind of denoted the inputs, outputs, and pieces with these red nodes, and then actual operations with blue nodes. So what this graph does is it says, all right, I'm going to take beta 1 and x1, and I'm going to multiply those. And then I'm going to take beta naught with the resulting product and sum that to get y. Right? So ultimately, that is just our linear regression equation from right up here. Okay. And why is this useful? Well, it turns out that when we start talking about neural networks, hopefully in about 40 minutes or so, and then if you move on past this and keep looking at or studying neural networks, it's pretty common to talk about them as computational graphs. It's also, for all the neural network libraries that I've worked with, you code them as computational graphs, so the engines that run them are coded as computational graphs. And a quick 10 seconds on why those are useful. They basically allow you to define this entire equation beforehand and then build in a lot of optimization procedures that can speed up your program. They also allow for or help with automatic differentiation. So you don't have to take any derivatives yourself. Okay. So some other kind of quick terminology updates. We're going to formalize the gradient descent procedure for simple linear regression in probably about 5 minutes. But before we get there, I'm going to take a kind of high-level overview of what we're going to do and discuss some neural net terminology. Oftentimes, we talk about gradient descent with neural nets using 2 major steps, and that's forward propagation and backward propagation. And the forward propagation step is really where we just calculate our predicted values, right? So we read our graph from left to right, and we use the equation that generates our predicted values to obtain those. So that's the forward propagation step. The backward propagation step is where we're going to read our graph from right to left, And that's where we're going to actually take the derivatives and use those derivatives to update the coefficients or perform that gradient descent step. Okay? So forward propagation, calculate our predicted values. Backward propagation, basically another term for gradient descent. Okay. Okay. So if we were to try to take our linear regression equation, this guy right up here, and perform gradient descent on it, what we do is end up calculating the derivatives. And we could just simply write those out, right? We do that when we solve for the closed form solution that we showed above. But what we're going to do is look at this, again, through the computational graph and calculate the derivatives that way, right? And specifically, we're going to use the chain rule. How many of you remember that chain rule from high school calculus? Awesome. Okay, so it turns out it's going to be incredibly useful because basically what we're going to figure out is that every single node in our graph can simply take something passed on from a prior part of the graph, then calculate its own internal derivative, and then pass that multiplication on backwards, right? And so when you build up these really complicated neural networks where a graph might span the entire screen, it's incredibly easy to modularize these calculations. And that's kind of what this chain rule allows us to do in this case. So if we wanted to take the chain rule here, and we know we want to get the derivatives for beta 1 and beta naught to update, then what we do is simply say, all right, I'm going to start out with my error, right? And ultimately, I want to know the derivative of the error with respect to beta naught and beta 1. But I start out with my error, and it's a function of my predicted values. So I take the derivative of the error with respect to the predicted values, right? That's the first step. And then I take the derivative of the predicted values with respect to each of my coefficients. Okay? And so you take these individual pieces, and then you multiply them together to get your full update step, which is a little bit different than we would do it in calculus, right? Or kind of the standard way we do it. Cool. So we'll move on to chapter 2 now, where we are going to actually walk through the calculation of those derivatives, and then we're going to code this up using NumPy. Okay. So in terms of formalizing the steps of our gradient descent procedure, and we're doing this just so we can kind of link it to the exact things we're coding up later on. We're going to have two major steps. The first is that we're going to randomly initialize some values for our beta naught and our beta 1. Right? We're just going to say, hey, I think maybe they're 0.5 and 0.5, or maybe they're 0.2 and 0.3. We're just going to pick some random values, and that's fine because once we start gradient descent, we will keep stepping iteratively in the direction of the true values. So we randomly initialize those values, and then the second step is kind of our iterative process. And that's where we're going to say, for some number of iterations, I'm going to do that forward propagation and backward propagation. Okay. So for some number of iterations, I'm going to calculate my predicted values, calculate the error for each of those predicted values, and then I'm going to calculate the gradients for each of those predicted values using that chain rule. And once I get all of those gradients, I'm going to actually update my coefficients, right? It's kind of vanilla flavored gradient descent. Okay. So in terms of our actual derivative calculations, maybe I should have asked you guys to do these, I don't know. But if we want to look at the derivative of the error with respect to our predicted values, we know that our error term is 1/2 times y minus y hat squared. And so we can calculate the derivative by bringing the 2 down. And then you just multiply the rest out, and you get the negative in front because we're taking it with respect to y hat. Then in terms of taking the derivative with respect to our predicted values of beta naught and beta 1, we know that this is just a 1 because it's got nothing in front, and this is x1. Right? Everybody follow that? Yeah. Cool. So to obtain our full update steps then, all we have to do is just plug these pieces in. Right? And you'll end up noting that the update step for beta naught is simply the negative of our the difference between our observed and predicted. And then it's that times our x values for beta 1. Okay. Star is multiplication, yes. Yep. Good to clarify, thank you. Okay, so now to the fun part, some actual code. Up here, this is just going to import everything we need. And today, to actually do an intro to neural nets and kind of just show the power of neural networks, we are fitting either perfectly linear data, perfectly separable data, or data that follows perfectly some generated function. So a little bit less practical than in the real world, but to kind of highlight the power of neural networks and show how useful they can be, that's what we're going to do. So up here, this just imports a function that will generate some simple linear data exactly, and this generates something that will plot that data. So we can run those. You'll get a matplotlib kind of setup warning if you're running this through the Docker container, but it's nothing to be alarmed about. And then next we have our code that generates this. And you'll see that we are basically just coding up the exact steps that we just talked about. Right? So in step 1, we are going to randomly initialize our values. And then this whole block consists of step 2. And we've got each of the 3 individual steps that we talked about. Right? So we calculate our predicted values. That just follows our equation. We calculate our errors. And then we calculate the gradient of those errors with respect to the coefficients and actually use those to update. Okay? So something that I haven't quite mentioned yet is the learning rate up here. And we're doing that just to take smaller steps with our coefficients so that our gradients don't quite explode and we actually do converge. So I'm going to run this cell, and then if we come down to this cell, what this is going to do is actually just generate the fake data that is basically this block here, and then this is going to perform that gradient descent procedure using forward propagation and backward propagation to learn the values of those coefficients. And so if we run this, and this ultimately what this is going to plot is our error over time. Okay, so it's effectively just showing us that, hey, we can get to 0 error, right? Which isn't terribly interesting if you take your errors and plot slightly different iterations. We'll say 300 to 500. It looks a little bit more interesting, right? We can actually tell we're learning. So is anybody excited or happy about this? Right, I know, it's linear regression. It's not that interesting in terms of like actually learning the values. But key takeaways here are the fact that we've kind of walked through this computational graph visual, and we have also started working through forward and backward propagation now and kind of started getting much more familiar with that terminology and kind of how that process works. So now we're going to move on to doing this in Theano. Who's ever worked with Theano before? Anybody? Okay. I have to admit I haven't coded a ton in actual raw Theano a lot. I've used Caras quite a bit, but Theano is something I'm much less familiar with. But Theano, from a high level, is basically something we're going to use to define a computational graph in code, and then we are going to just let it run, and it's under the hood because it is a kind of computational graph library, going to perform some optimizations that will speed up our programs. And then ultimately, what we'll also see, and this is actually probably the much more fun part, is that it has automatic differentiation built in. So we don't, in the future, if we don't want to, have to calculate derivatives at all. Okay? Okay. So just real quick, recall our forward and backward propagation steps. That's what we're going to end up coding up. We've got our kind of standard import statements. Here are maybe the 2 different ones this time. We're importing tensor library from Theano, which helps you deal with a lot of your matrix multiplications and vector calculations, and then just the Theano package as a whole. So we're going to run that, and then we'll come down here, and this get Theano graph is basically, from a high level, going to do exactly what that function we just looked at with NumPy did. Right? It's going to build up this set of steps that performs forward and backward propagation. There's going to be a slight difference in the fact that this is only going to perform 1 iteration, and the function we did last time performed a bunch of them, but it's simply a matter of creating a loop later on after we return this. Okay, so one of the key takeaways for Theano and any kind of computational graph library, so if you ever work with TensorFlow, it's this similar thing, is that when you're building things up, it's often the case that it puts off computation until the last possible minute, right? Because ultimately what you're just doing is defining this computational graph, you're defining this plan of attack or this recipe, and then it's not going to execute it until it needs to. And so, we have the same steps as before, except now we are, in some places, not actually generating raw data, we're just generating placeholders. So specifically here with XS and YS, we're just generating placeholders telling Faaaan, hey, at some point later, I'm going to fill in data associated with those, and you can expect them to be of this type float64. But you can specify types, And then we're still going to randomly initialize variables for our beta naught and beta 1. Key thing to note here is that this shared method, or this denotion of these variables as shared, is what allows them to be used over and over again and actually updated. That's kind of something that's kind of a gotcha with Faaaan or TensorFlow if you use it, is that you have to make sure that these variables are updatable, or else they're just kind of treated as static and constant. So I would make sure to keep that in mind. Okay, and then after that, this is just kind of defining the rest of our gradient descent procedure. This generates our predictions, this generates our error, and then this is kind of the really money line here, where we're able to take advantage of Theano's automatic differentiation, right? So here we just have to say, all right, Faaaan, take the gradient with respect to take the gradient of the error with respect to beta 1 or beta naught and beta 1, right? And then it'll just give me back out these derivatives. And then I have to use those derivatives later to perform an update step, and we'll get to that in just a second. But does this make sense? Good so far? Okay, cool. So finally what we're going to do is take basically this entire computational graph that we just built, and we're going to throw it into a Theano.function call. And what that's going to do is actually define this returnable object, this function, that we can later call to perform one iteration of gradient descent. Okay, and it's going to perform that in the way that we've specified. And what we have to do with this Theano function is tell it what's going to be input, right? And we know we want x's and y's because that's going to be used to train. Outputs, those can really be anything we want. If we don't want our function to output anything, but we just want it to train, then we can do that. But more likely than not, we either want the error, the y-hats, or the particular weight values. And then finally, and this is where we're able to actually use those derivatives, is this updates. And this updates takes an iterable of tuples, where the first item in the tuple is what you're updating. So for this first one, I'm updating beta naught. And then the second item is what you want it to update with. Right? So at every iteration of the gradient descent procedure, I want to say replace beta naught with beta naught minus the learning rate times the gradient. Right? And then the same thing with beta 1. So if I hit enter there, then I come down here and I run this code again. This is the same code. I didn't run the import cell. Oops. Okay, I run the same code here, which again just generates some fake data, follows a simple linear relationship, gets the actual Theano graph, and then starts iterating over it. We'll end up finding out that we're able to, again, get 0 error, right? So we can do this in NumPy and now Theano, so now we're twice as useful. But not really, because it's, linear regression. Okay. Any questions at this point before we kind of jump into Caras? Okay, cool. I think we're right on time, too. We're about at half an hour. Okay, does anybody have any experience with Caras? No? Okay, cool. Then this is a great time to make a plug for Caras. So like I've shown here, you can define neural networks in NumPy. You can define them in Theano. There's TensorFlow. There's loads of other frameworks as well, too, that you can use. One of my personal favorites is Caras, and as we'll see here as we go through this, it's because it has an incredibly easy interface to use. It's really, really easy to build up incredibly complex networks, in a pretty short amount of time. And it's also fairly extensive. And it's not often that leading research in the field gets done and Caras doesn't keep up. So if you start getting really deep into neural networks and you get to be doing a lot of custom stuff, it might be the case that digging under the hood and using Faaaan or TensorFlow is useful and necessary. But I think for 90% of problems, Caras should be your go-to. Okay, so Caras is a neural networks library that runs on top of Faaaan or TensorFlow. So basically what it has said is, I'm going to code up a bunch of stuff under the hood in Faaaan or TensorFlow, kind of like we just did, but then give us wrappers around that stuff so that we can easily construct things and have a nicer interface and iterate more quickly with our algorithms. So here's our forward and backward propagation steps again. And then we're going to get to the code. So we've got a lot of potentially new stuff here, but this is ultimately going to specify just the same parts of our simple linear regression equation and gradient descent procedure that we looked at previously. So we will look here at our actual procedure that defines a model. And the first thing you'll notice is that the code's a lot shorter, right? I think this step, or parts of this, it takes 2 lines where previously it took 5. So in terms of diving in, we have the same learning rate that we've had before. Here we again specify a placeholder, but instead of specifying a placeholder for our inputs and outputs, we just have to specify a placeholder for our inputs. Okay, and we're going to end up filling that in later. After that, we are going to define the equation that generates our predictions. And previously, we actually had to hard code that up, right? We had to code in the y hats is equal to beta naught plus beta 1 times x1. And here, what we're going to do is use what's called a dense layer. And we're going to get more into the terminology of that as we actually look at neural networks in 20 minutes, half hour. But basically what this is going to do is say, I want dimensionality, I want my output dimensionality to be 1, and I want to take a weighted sum of the inputs to this node here and just apply a linear activation to it, which is just the identity function. Okay, so you take in your x's and you apply an identity function to a weighted sum of their inputs, so you end up getting out ys, and that's your linear regression equation. Okay. So that's, in essence, kind of the forward propagation step. And then we have a kind of middle step that's not really part of the forward propagation or backward propagation. It's just where we define an actual Python object that we can use to later run this gradient descent procedure. And so this is just a model that's imported from Caras, and we have to specify input and output. And then finally, after we specify that model, what we have to do is come down here and call compile on it and specify a loss and an optimizer. Okay. So we've been using mean squared error up to this point, and we've also been using stochastic gradient descent. How many of you are familiar with other flavors of gradient descent? Okay. For anybody not, so far we've been talking about just kind of iteratively taking slow steps towards down our error curve. There are a number of other complicated flavors of gradient descent that just take kind of momentous steps towards the bottom of your error curve. So if you're taking steps and you keep finding you're going in the right direction or the same direction, you take bigger steps. If you find that you are constantly taking steps in very different directions, maybe you slow down, things like that. So Caras gives you the ability to specify all of those as well. But right now, we're just going to keep using the standard stochastic gradient descent that we talked about. Okay, so if we run that, we come down here, and we have effectively the same thing that we've run before, but I want to highlight one part of this, and that's what's going to actually end up running this model. So in this line here, we actually get the model that returns it to us. You can ignore these parts. And then this fit method is what we actually use to perform the gradient descent. And for that, we have to specify inputs, outputs, and then some additional parameters. And here, we're just specifying how many iterations to do. We're specifying that we don't want it to print out a bunch of stuff. And Batch size is something that might be used for batch gradient descent, where you're not doing the entire data set all at once, but kind of small chunks of it and then performing updates. But right now, we just want it to do the entire data set. So that's what we're having it do. So we can see that, again, we get 0 error. So now we're going to jump to chapter 4 of this. So if we go back, you should be able to navigate this in your browser. Cool. All right. So what we're going to do now is actually build what we're going to call our first true neural network. And there are kind of differing definitions of what people will label as a true neural network. But here I'm calling a true network anything with what's called a hidden layer. And a hidden layer is defined to be anything that's not your input layer or your output layer. Okay? So before, we basically just had some x that we were taking in, along with our intercept, which was up here, and then we were just feeding it in straight to here and outputting it. But now we're going to have this intermediary step, this hidden layer, and what it's going to do is take a weighted sum of its inputs, apply some function to it, and then pass that on to kind of the next layer, and that next layer is going to do the same thing. So what we actually need to do before we do that, though, is build in some connectivity to it. Okay. And so if we build in the connections to it, our graph gets a little bit more cluttered, but this still isn't too bad. And this is going to kind of denote what our graph looks like and how we're going to end up coding this up, right? So every single node in each layer is connected to every single node in the subsequent layer. Right? So we're still, in that case, reading left to right. And what we're saying is this first node is connected to both of these nodes, and this node is connected to this node. It's a little bit hard to picture here because we've got so few nodes, but you can imagine that if you had more, right, we'd have a lot more arrows flying around. And in terms of a piece of terminology here, these are what's known as fully connected feed-forward neural networks. The fully connected comes from the fact that each node in a previous layer is connected to every node in a subsequent layer. And the feed-forward part comes from the fact that everything is flowing from left to right. Right? You can imagine that we could code something that would pass this input back to this, or would pass this input down to this, or something crazy like that. But right now, we're just going left to right. And so that's why it's labeled as a feed-forward, fully connected neural network. Okay, so if we wanted to denote this formulaically, this is what we'd end up seeing, right? We can just do that. But I'm going to posit here that this is just linear regression. So we're still not really doing anything that we haven't done already today. And so if we wanted to show that, what we could say is that W31, this weight right here is equal to 1, and then we get to this equation here, and then if we say that this weight here is beta 1 and this is beta naught, we're back to our simple linear regression equation. Okay, so who's ready to move past simple linear regression? Cool, me too. Okay, so what we're going to do that is we are going to take those functions that we're applying to the weighted sum of the inputs in that hidden layer, and we're going to change them. We're no longer going to just use the identity function and say, hey, I'm going to take a weighted sum of my inputs, throw it back out as output. Instead, what we're going to do is apply the sigmoid function, more also commonly known as the logistic function. In neural networks land, those two terms are often used interchangeably, but I do realize they can be different mathematical formulas. So now if we wanted to look at a mathematical depiction of our neural network, it would look something like this. Okay? And the power in this is that we're now able to automatically capture nonlinearities in our data. Right? And we don't have to specify them. You could argue that with simple linear regression or multiple linear regression, we can specify that we want x squared to be in our equation, or we want some multiplicative terms to be in our equation, et cetera, right? We can specify nonlinearities. But here, What I'm telling you is that all we can specify this sigmoid function, and then it will just pick up nonlinearities for us. And we don't have to be explicit about what those nonlinearities are, which is pretty powerful, I think. Okay. So we are, again, going to fit our neural network with squared error, right? Which is fitting because we are still using the identity activation up here in our output layer. Okay. If we changed this function over here to a sigmoid, we'd, in that sense, be doing something like logistic regression, and we'd probably want to use log loss or cross entropy. Okay. 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 So in terms of the derivatives, we're going to make some quick notational changes, and I'm going to go through these, I think, somewhat quickly just so we can get to code. We're going to denote the weighted sum of inputs to each node in the first layer with z's, right? And we're going to have subscripts and superscripts for those. So our equation then becomes this, and this just makes it a little bit easier when we're doing that chain rule in the backpropagation step to make explicit the exact derivatives we need to calculate. Because since we no longer have that identity function here, we have to calculate the derivative of this function with respect to its input. Right? Before it was just 1. Okay. So again, we'll still have, though, forward propagation and backward propagation steps. With the forward propagation step, we'll do what we did before, but we now have the extra step of a hidden layer and nonlinear activations. And then with backward propagation, we will calculate all these derivatives and apply the chain rule to make updates. We'll walk through one here. We'll just say this first one up here. So cool. We've got our equation right up here. We're going to look at this derivative down here. Ultimately, we get this derivative by following back through the graph. So, actually, yeah, or the equation. And we'll fall back to the equation. So we know that weight 112 is part of Z12, and so we ultimately have to get back there. So we start off with our error, take the derivative with respect to our predicted values. Our predicted values, we get to Z1 through the function applied to Z1, so we have to take the derivative with respect to that. Then we have to take the derivative of that function with respect to its input. That's where I mentioned the difference between that and the identity. And then finally, we have to take the derivative of that input with respect to the weight. Okay. Okay, any questions before we jump to code? Okay. Okay. So this is a kind of formalized version of our gradient descent procedure. It's the same procedure we looked at before. We just have more weights now. And we've moved from calling our coefficients to weights, but in essence, they're the same thing. And then our biases are the intercept. That's what these B's often are referred to as. Okay. So we're still going to randomly initialize values for our weights and our biases, now is what we're calling them. And oftentimes the weights are initialized following uniform or normal distribution or kind of some variant of that, whereas the biases are initialized with zeros. So we'll follow something similar. And then our second step, that's still going to be our iterative step, where we just iterate over our forward and backward propagation steps. And so we perform our forward propagation still by calculating our predicted values. After that, we calculate our error, and here we're still using mean squared error. And then for every single observation, we're going to have to calculate all of these gradients, right? And then we're going to use them to update our weights. Okay. Okay, so let's look again just at this single weight calculation, and we'll kind of walk through the derivatives for those, and then hopefully those kind of extend to others. So the first thing we need is the derivative of the error with respect to our predicted values. That's here, right? We saw that before. The second thing we need is the derivative of the predicted value with respect to the first input node weighted sum with the function applied. And we'll note that that's just that weight that gets multiplied by it. No, equation's not up there. Okay. After that, we need the derivative that is here. And it turns out the derivative of the sigmoid function is simply the sigmoid function applied to its inputs times 1 minus the sigmoid function applied to its inputs. So it actually turns out to be a really nice derivative for us. And then finally, we're back to the derivative of the input with respect to that weight, and that's simply just our x's. Okay, so we plug these all back in. We'll get all of our update steps, and then these update steps are what we'll actually code up. No one likes to stare at math too long, I don't think, so we're going to keep going. But those are there. Happy to talk about them if you guys would like to at any point. Okay. So we're going to go ahead and run this first part. We're back to NumPy. And that's just, again, to show how this works with NumPy, so then we can kind of work to Theano and then Caras as well. So we're, again, building what I'm calling a learn with gradient descent function. And we're basically just going to define the steps of that gradient descent procedure in code. And so our first step here, step 1, is where we randomly initialize everything. I have moved away from coding individual coefficient or weight variables and just coding matrices or vectors for them instead. So you'll note that that's a change. So this W2 here is all the weights going from the input layer to the hidden layer. And then this W3 is all the weights going from the hidden layer to the output layer. Okay, and then the same with the biases. So we have all our initialized weights and biases, and then we come down and we perform our iterative procedure. Okay. And so there's a couple of steps to this that are just maybe formulated in a little bit different of a way to hopefully make it clear. So first we're going to calculate the weighted sums that go into each of the nodes at layer 2. And then next we're going to apply that function, find our predicted values, right? That's our forward propagation step. Then in these steps here, we are going to calculate the errors, calculate the gradients using those errors and all of our weight matrices, and then actually perform those updates. And then finally, we're going to return the predicted values this time because we're no longer looking at error curves because that's no fun. We're actually going to look at the functions we learn. Okay, so let's run that. And then down here, we've coded up something that will actually run through this procedure. And there are 4 graphs that end up popping up. And the reason for that is the following. It turns out that neural network that we define with 2 hidden nodes, or 2 nodes in that hidden layer, it's not that powerful. It actually doesn't learn that much. It's hard for it to learn. It's hard for it to pick up the relationships in this sign function that we're modeling. So what we're going to do is just arbitrarily increase the size of that hidden layer. Right? And that's actually baked into this function above. So it takes in a parameter called h-layer size or hidden layer size that you can pass in. And so when we come down here, I am running through a couple different values for that hidden layer size, namely 2, 10, 100, and 250. Okay? And because of the way that we've built that function using matrices and using vectors, it is that easy to just pass in a different number as a parameter and have it scale up the size of our network. And in terms of some terminology, when we add more nodes to a hidden layer, that's often referred to as making a neural network wider. Deeper tends to refer to adding hidden layers to a neural network. This is running, right? Okay. It's taking quite a while. Okay, cool. So ultimately now, what we see is that as we add more hidden nodes, or more nodes in our hidden layer, our network has much more representational power. right? It's able to actually learn these functions much more easily. Excuse me. Okay, so what I've done here is actually just plotted the true function, which is in red, and the network generated function in blue from different sized networks. I'm trying to get the best coverage here. Okay, so this first plot here, we have our 2, right? And that really doesn't generate anything more for us than a sigmoid function, right? Which is not too surprising because we have those sigmoid activations in the hidden layer, but also isn't helpful because it hasn't learned anything. So in the next one, we move to 10, and we see that it's doing a little bit better, particularly if we look at the center parts here, but it's still not doing that well. And then finally we move to 100, and we start to see that it gets more flexible, it's starting to actually pick things up. And then finally, by the time we get to 250, it's doing reasonably well and probably giving us a result that we might actually want to keep. Okay, and we would see this if we did it with any kind of arbitrary mathematical function, right? This is x to the 4th. So again, we have 2 nodes, 10 nodes, 100 nodes, and 250 nodes. And we see that as we add more nodes into that hidden layer, the network's much more easily able to learn that function. Okay, and ultimately what this allows us to know is that neural networks have this kind of universality, right? They have this universal applicability in terms of learning functions. So there are places online, and there's a link actually at the bottom of this notebook to, has anybody ever perused Neural Networks and Deep Learning by Michael Nielsen? Okay, excellent book. It's got an excellent chapter on the representational power of neural networks and the universality theorem. But effectively, at some point, what he shows is that if you add enough nodes to a hidden layer, you get basically a number of these that just run next to each other, right? And each one is able to learn to spike at the exact right point, and then you're able to learn arbitrary functions. And so I would guess that at that far out, they just haven't learned yet, or there's not enough nodes to cover that part of, yeah. Okay, so in Theano, we're going to have kind of the same magical power that we had before to have automatic differentiation and not have to hard code the derivatives. So again, we have our forward and backward propagation steps. So those are the exact same as before. And then we get down to our code. So we're again just defining a function called getTheanoGraph. It's the same name that we've used before and has similar steps. We're going to start off, we're going to generate placeholders for our data. Next, we're going to randomly initialize values for our weights and biases. I'll again highlight that we need to define them as shared so that they actually get updated through iterations of our gradient descent procedure. After that, we're going to generate the equations that actually give us predictions. And the difference here between what we did earlier is that we are now going to have to add in this kind of nonlinear activation function, right? So we're still going to say, hey, take a weight at some of our inputs, and then we're going to apply this function, which we didn't have to do in our last Theano implementation. Okay, but that's just the Theano implementation of that sigmoid function. It's equivalent to the NumPy one that we looked at last notebook. Okay, so then we're going to, again, get our errors. Then we're going to tell Theano to take the gradient of those errors with respect to all of our weights and biases, and then use those to update. And here, there's a slight difference in the actual updates. I've just made a list and appended everything to them as opposed to passing them right into the Theano.function. But that's perfectly valid. All right, so I will, I actually don't think I'm gonna run this because it will take too long to run. I'll instead just show the results for now. We can, again, see that this follows the same pattern. Right, we see that as we go from 2 to 10 to 100 to 250, and we give the network more representational power in that hidden layer, it's able to much more readily learn that function. Right, to the point where here we're extremely accurate. is there any other function other than sigmoid? Yes, so that's a great question. Since we have the graphs up here, you can put any function you want into these nodes, so these are called these functions are often referred to as activation functions. I think you've heard me say that now. But you can put any activation function you want in there, and there are some very common ones that are used with neural networks that Faaaan, TensorFlow, and Caras all offer built-in, and it's pretty easy to switch between. This is actually sigmoids are actually not really used at this point in time anymore. They're much more popular and common activation functions to use. It's just really easy to demonstrate with these. Cool. Thanks. Anything else? Right. Yep. There are a lot of different things you could do to not have to have this many parameters to fit these functions. So one of the things you could do is add more layers, and that's where we just have one now, but maybe you have 2 or 3 or 4 hidden layers. There are some troubles there in terms of gradients actually back propagating, but there are tricks that have been figured out how to deal with that. So that's one of the things you can do. Different optimizers, which are different variations of gradient descent that I kind of hinted at earlier. Those are extremely good ways also to not have to have this kind of representational power. Actually, that'll help a little bit, but actually not that much. Sorry. So that's a trick in terms of, there are other tips and tricks too, which happy to talk about after if you'd like, or offline. Anything else? Okay. Cool. We will look at the Caras version now, and then I'll kind of set you loose, and we'll come back for questions at the end. Okay. So with Caras, we will jump right down to the actual code to define it. And what you'll notice is that there are basically 2 minor differences, or 1 major and 1 minor. And the first major difference here is that we've actually added another dense object here, or another dense layer. Okay, and that's going to be our hidden layer. And in terms of dense, I said earlier we'd talk about that more. When you're defining a dense layer here, what that's saying is I want it to be fully connected. Right? So I want every node in the layer that's coming into this dense layer to be connected to it. Right? And so that's all that dense refers to. There are other kinds of layers that you can have that aren't specified in that way. In terms of the dense layer, we have to pass in the inputs as if it's a function call. And then we again have to specify a number of nodes in it. That's the hidden layer size, as well as an activation function. And here we're just specifying the sigmoid activation function that we've coded up in NumPy and Theano. Okay? Other than that, everything else looks exactly the same, except for the name shallow network here. Before we called it a linear model, it turns out that neural networks with hidden layers are often referred to as shallow neural networks, and when you get to 2+, deeper neural networks. There might be some debate on whether it's 2 or 3, 4, but somewhere around there. Okay, and then per as before that we saw with NumPy and Theano, we are able to learn all of these. We're able to learn this function as well as the x to the 4th function, and we again see that as we add more nodes, we get more representational power. So the last thing I want to do before giving you some time to play around with this or just otherwise ask questions is note that if you would like to, with the gen_pow_x function, which generated our x to the 4th data, you can input some other power if you want. Although odd and even powers all look incredibly similar at those scales. But you can input that and see that the network is also able to learn that. And then with the gen trigonometric function up here, you can also put in tanh and cosine. You can see that it's able to learn that. And if you play around with those, what you'll ultimately get to is something like this with each of those functions. Cool. Okay. I'll let you guys just play around. I'll be here for the rest of the day. around here for the next 25 minutes. Thank you.